This tutorial will illustrate how to set up a model for a response spectrum analysis in ETABS. However, before we do this, let's discuss what a response spectrum analysis is. Response spectrum analyses are typically used for performing seismic analysis. Response spectrum analysis calculates the maximum response values in each mode of the structure from a spectrum curve and then combines these responses using modal superposition. These input spectra might be for a smooth spectrum like codes used to describe a range of earthquakes, or spectra for a specific earthquake. Spectra curves classically plot period on the horizontal axis and acceleration on the vertical axis, and may consist of multiple curves for different levels of damping. A response spectrum analysis seeks to determine the likely maximum response of a structure when subjected to the pseudo-acceleration of a response spectrum curve. An easy way to idealize a response spectrum curve is as follows. A whole series of single degree of freedom oscillators at a given damping level are subjected to a time history analysis. The peak relative displacement values from each oscillator are determined and then converted into pseudo-spectral acceleration, PSA, by multiplying by the natural frequency squared. These points are then plotted on the ordinate against the period of the oscillator on the abscissa. Connecting these points leads to a response spectrum curve for a given damping. Our example here is for a single damping, let's say 5% of critical, but different curves could be generated for different levels of damping. This curve represents our seismic input. Response spectrum analysis is based on modal superposition. Modes of the structure are calculated, and then the corresponding pseudo-spectral acceleration for each mode is determined from the response spectrum curve that matches the damping of the mode. Converting the pseudo-spectral acceleration into displacement and then using the mode shape along with the modal participation factor, forces and stresses may also be determined for each mode. However, a building response is not made up of a single mode, but the response of many modes, so the response from the different modes must be combined. One way might be to simply absolute add all the responses together. This is not very realistic as it assumes all modes peak at the same time, same direction. A more common way is to combine the modes using some type of square root sum of the squares. A more statistical approach, if you will. However, the squaring of terms means that the reported results will always be positive. So it is important to understand that these results can range to the negative values as well. In addition, there is no correspondence between two response quantities, like there would be in a time history analysis. With that bit of background, let's start our analysis. Our model will consist of a simple two-story, 1 bay by 1 bay concrete building. We start by determining what modes will be used. This is done using the define modal cases command. For our modal case, we can use either the classic eigenmodes, which are the free vibration modes, or the Ritz modes, which are load-dependent vectors. Ritz vectors are often a better choice when doing modal superposition, but for this example, we will stick with eigen. We will use the default mass source, which in this case is simply the mass of the structure, although other mass sources could be defined that might include things such as equipment mass. ETABS also allows for the stiffness used in the generation of the modes to be modified by p delta or a nonlinear analysis. In this model, we are going to use the stiffness as altered by p delta. And in this case, we'll use the p-delta determined from the non-iterative mass technique. We could also ask the program to determine static correction modes, which can be important when modeling supports that are very stiff. These are sometimes referred to as missing mass modes. However, we will skip this here. In the other parameters section, we can specify the maximum and minimum number of modes to be calculated. The response spectrum analysis will only use the modes that are actually found. Because our building is being modeled using rigid diaphragms, and we are not interested in vertical excitation, we will only have 3 mass degrees of freedom per floor, 2 translational and 1 rotational. Therefore, 6 modes should be adequate to capture the response that we are interested in, so the default of 12 should be fine. We could also adjust the range of the frequencies to be sought by using the shift and cutoff parameters. This could be useful if we want to force the program to search for building modes that are higher frequency, such as to match the input from a piece of vibrating equipment. However, because our analysis is for seismic loads, the lower frequency modes are important, and thus it is appropriate to use the defaults of 0. The convergence tolerance determines how close successive eigenvalue iterations need to be before the program can move on to the next mode. For this case, the default is satisfactory. Lastly, we will leave the auto frequency shifting option on. This will often speed up the solution and improve accuracy. Next, we will define the input response spectrum to be used. We have many to choose from. And in this case, we will use the ASCE 7-10 curve. We will give the function the name ASCE RS. Note the function damping ratio. This identifies the damping used to generate this curve. If this value is different than the resulting damping used for the building, this curve will be adjusted to match the damping level of the structure. That is, if the defined curve we are using is at 5%, as shown here, but the modal damping we are using for our building is 2%, the curve will be scaled up so that the response will be greater with the reduced damping of the structure. For this response spectrum, the parameters can be user-defined or determined automatically by the program based on either latitude, longitude, or by zip code. For this example, we will use user-specified and enter an S sub s of 1.99 and an S sub 1 of 0.65. We will adjust the site class to C, which is for very dense soil and soft rock. Points for the curve are displayed here. The period is shown on the abscissa and acceleration in G units on the ordinate. We can move the cursor over the graph to obtain the coordinates at any point. Next, we define a load case to include the response spectrum analysis. We will call the new case RS, and we'll select response spectrum as the type. We will apply our response spectrum as an acceleration in the U1 direction, using the previously defined ASCE curve. Next, we will apply a scale factor. This might be to convert from G to inch units or to apply code factors such as R over I. We are also going to apply the same response spectrum in the orthogonal U2 direction. This may seem somewhat unusual, but we will explain our logic a bit later. If we click the Advanced checkbox, we could adjust the angle at which our functions are applied. The analysis will use modes defined by the modal case, and we have a number of ways that we may combine the modes for a given direction, including CQC, square root sum of the squares, absolute sum, general modal combination, and others, but we will use the complete quadratic combination here. If we wish for the amount of periodic and rigid response to be interpolated between F1 and F2, we can check the Include Rigid Response checkbox. In order for this interpolation to occur, F2 must be greater than or equal to F1 and non-zero. We will not use this option here. Since we are applying excitation in more than one direction in a single load case, we need to specify how to combine the directional responses using either SRSS, absolute, or CQ-C3. We will use square root sum of the squares. Now we will discuss why we use SRSS along with the same response spectrum functions in both directions. Design codes often require that members be designed for 100% of the seismic load in one direction and a lesser amount, say 30 or 40%, in the orthogonal direction. However, to do this effectively assumes that you know the critical direction of the earthquake motion, as well as the principal axes of the building, which is typically not the case. In theory, in order to capture the maximum response in a member, the orthogonal earthquake pairs should be rotated through all possible angles. A substantial computational effort. However, ETABS offers a better way. By using the same function in both orthogonal directions and then using SRSS for the directional combination, the maximum may be captured using a single analysis run. And because this technique is coordinate system independent, any orthogonal orientation will work. A big time saver. For the damping, we have a number of options, but we will use the default of 5% constant damping. Because our model utilizes rigid diaphragms, and most codes require that accidental torsion be applied when using rigid diaphragms, we will apply a diaphragm eccentricity of 5% to both floors, which will apply an additional moment about the center of mass. Now we will switch off the extrusions and get ready to run the analysis. We will run only the modal and response spectrum cases. When the analysis is complete, the first mode is displayed. The second mode is another translational mode. The third mode is rotational. The fourth and fifth are both translational, and the sixth is another rotational mode. Note that there are no more than 6 modes. As we anticipated, 2 floors with 3 mass degrees of freedom. The response spectrum load case has the following deformed shape. It is a single response based on the superposition of the modes. We can show the base reactions by going to the Display Forces Supports command. We will select the two horizontal components. Note that the forces are symmetric. We can also view output in tabular form. Starting with joint displacements. Note that all values are positive. This is due to how modal results are combined. Returning to the tables, we will display diaphragm accelerations, important for occupant and equipment studies. Returning to the tables once more, we will look at the participating mass ratios. Participating mass ratios denote how much mass we have utilized in our analysis, and the closer the summation is to 1, the better. Note that in our case, by the last mode, our participating ratios all do sum up to 1. This concludes this tutorial on creating a response spectrum analysis in ETABS.